Welcome back to another highly requested video on AS Physics pressure. This video covers 10 frequently pressured questions from past exams, so grab your notebook and calculator and let's get started. First question is from October-November 13, paper 11, question 22. Water in a bath varies in depth from 20 centimeters at the shallow end to 30 centimeters at the end with the plug, 20 to 30. The density of the water is 1,000 kilograms per cubic meter. What is the pressure of the water acting on the plug? So what we are going to be looking is this section and the water pressure acting on the plug. To calculate this pressure, right on the plug, we are using the formula for pressure in a liquid. So the pressure at the plug is equal to the density of the water times G times the height from the water surface to the plug. So is doing the value substitutions, 1000 times 9.81 times the height in meter, 0.03. And the answer of this product is 2,943 Pascal. So the closest answer is C. Second question. The diagram shows a rectangular block of mass 8.2 kilograms immersed in seawater of density 1.10 times 10 to the 3 kilograms per cubic meter. What is the difference in pressure between the top and bottom surfaces of the block? To answer this question, we are using the pressure difference equation of hydrostatic pressure, which is the product of the density of the seawater times G times the difference in height. So the density of the seawater was provided, which is 1.1 times 10 to the 3. And this is the acceleration of gravity. And this is the difference in height, 2.2 minus 2. So the product of this equation is 2.2 times 10 to the 3 Pascal, which is the answer B. Next question from May-June 11, paper 12. The diagram shows two vessels, P and Q, both with sides inclined at 45 degrees. So 45 degrees here, 45 degrees here. Vessel P tapers outward and vessel Q tapers inward as shown. Both vessels contain a liquid. The depth of the liquid in the vessels is the same. The liquid in vessel P is twice as dense as the liquid in vessel Q. What is the ratio of the pressure due to the liquid on the base of P and the pressure due to the liquid on the base of Q? This line represents the pressure P1 on both vessels at the surface. The second line represents the pressure at level P2, and the third line is the pressure P3 at the base of both vessels. The pressure P1 at the same level in vessels P and Q is the same. Similarly, the pressure at level P2 and the pressure at the base of the vessels P3 is also the same, regardless of the shape of the vessels. So here the question is asking what is the pressure at the base of the vessels P and Q. We know the pressure P depends only on the depth, the density of the liquid, and the acceleration of gravity. Therefore, the pressure at the base of the liquid P is equal to the density of the liquid P times G times the depth, which is at the base of the vessel. Likewise, the pressure of liquid Q is equal to the density of Q times G times the depth or height. So, it's asking for the ratio, P over Q. So, however, the question is saying the liquid in vessel P is twice as dense as the liquid in vessel Q, which means that the density at P is 2 times the density of vessel Q. So now we are going to cancel the variables rho key, G, and H. What is left? 2 over 1. So the answer for this question is option A, 2 over 1. Next question is from May, June 11, paper 11, question 19. 1.5 cubic meter of water is mixed with 0.5 cubic meter of alcohol. The density of water is 1,000 kilograms per cubic meter, and the density of alcohol is 800 kilograms per cubic meter. What is the density of the mixture with volume 2 cubic meter? To answer this question, we need to calculate the density of the mixture, which is the total mass of the mixture divided by the total volume of the mixture. The total volume of the mixture is 2 cubic meter. Now we need to calculate the total mass of the mixture. To calculate the total mass of the mixture, we are going to calculate the mass of the water and the mass of the oil separately. So here we have the density of the water and the volume of the water. So the product is 1,500 kilograms. Now the density of the alcohol is 800. The volume of the alcohol is 0.5. And the product is 400 kilograms. So the total mass of the mixture is the mass of the water plus the mass of the alcohol, which is 1,900 kilograms. Now back to our original formula. The total mass of the mixture is 1,900 kilograms, and the result of this is 950 kilograms per cubic meter. So this is the density of the mixture. So the correct option is D. The next question is from October-November 17, paper 11, question 12. A block is submerged vertically in a liquid. The 4 diagrams show to scale the forces exerted by the liquid on the block. Which diagram correctly shows a possible situation as viewed from the side? Let me relate the forces, the arrows, with pressure. So we know the pressure in a liquid increases with depth. Pressure of a liquid is equal to the density of the liquid times G times height. To answer these questions, let's analyze the arrows around the submerged block. The arrows on the top of the block must be smaller than those at the bottom because pressure increases with depth. So option A, the arrows are smaller than the bottom ones. Same as B, same as C, same as D. Next. The arrows on the sides of the block should increase in size with depth and must be equal on both sides for balance. So let's take a look on A. Yes, it's increasing and they are equal on both sides. At B option, no arrows on the sides. So now we are going to eliminate B. C, the arrows are increasing in size. They are both the same, like on the both sides they are the same. Correct. D, the arrows are not increasing size, even though both sides arrows are the same. So we are going to eliminate D as well. Goodbye. Now we have option A and option C left. Each one is correct. So that's the trick part. Look at this. The arrows at the corners of the block must match the size of the adjacent vertical arrows. So here is the vertical arrow. So is the same. This option C, not the same. So we are going to eliminate option C, and the correct answer is A. Question from October-November 15, paper 12, question 20. The diagram shows the cross-sectional area of an Olympic-sized swimming pool filled with water. It's not drawn to scale. The density of the water is 1,000 kilograms per cubic meter. What is the difference in pressure between X and Y? It's just asking the difference in pressure. To calculate this, we need to use the formula of pressure in liquid. Is the density of the water, or the liquid in this case is water, times G times the difference in height. So the difference in height here, X is at 2.35 and Y is at 2. So 2.35 minus 2. So the answer of this product of all those three elements here is 3,422.5 Pascal. The best match is the answer B. This question is from February-March 24, paper 12, question 12. A borehole of depth 2,000 meters contains both oil and water as shown. The pressure due to the liquids at the bottom of the borehole is 17.5 megapascals. The density of the oil is 830 kilograms per cubic meter, and the density of the water is 1,000 kilograms per cubic meter. What is the depth X of the oil? For those of you that don't know what is a borehole, is a deep, narrow hole drilled into the ground to extract natural resources such as water, oil, or gas. Couple of applications is water extraction. Boreholes are used for accessing groundwater for drinking, irrigation, or industrial use. And also for oil and gas, boreholes are drilled into reservoirs to extract crude oil and natural gas for energy production. Now you know. So back to our diagram. So the pressure at the bottom of the borehole is 17.5 times 10 to the 6 pascals. The pressure at the oil section is the density of the oil times G times the height of the oil, in this case X. And the pressure of the water is the density of the water times G times the height of the water, which is 2000 minus X. Now the pressure at the bottom is equal to the pressure above, the pressure in this column, which is the pressure above the bottom, which we have here the pressure of the water and the pressure of the oil. So doing the substitutions, the pressure at the bottom was given, and the pressure of the water is this section right here, plus the pressure of the oil, which is this one. Now, doing the substitutions, we have that the density of the oil was provided, the density of the water was provided, and here we have the density of the water, the density of the oil, and doing the distribution in these parentheses. So the result here is just follow along with my math. And here we have moving around, because what I want to calculate is the value of X. So the value of X is 1,271.2 meters. So I know I went a little bit quick on this, but it's right here in front of you. So you just follow along my math with yours. It's just kind of basic algebra and value substitutions. So the best answer for this question is option D. The next question is from October-November 19, paper 11, question 11. An object of weight W is suspended from a Newton meter. So here is the mark P, right? When the object is completely immersed in water, the Newton meter reads P. When the object is completely immersed in oil, the Newton meter reads Q. What is the ratio between the density of the oil and the density of water? So let's take a look on these diagrams side by side. So here is a cube immersed in water and the same cube immersed in oil. And we have 2 marks on the spring scale. So we are going to draw the free body diagram. So this is the weight of the block. This is the force that is marked on the spring scale, P. But because it's submerged in liquid, so we have the upthrust force. Considering this scenario is in equilibrium, so the sum of forces up is equal to the sum of forces down. So we have up, U plus P, and down we have the weight. We need to rearrange these in terms of the density of the water. So the formula here for upthrust force in terms of density of the water is density of the water times G times the volume displaced, which is the volume of the cube. So I want to rearrange this equation in terms of the density of the water. So this is what we have. Now let's work on the other diagram. So again, we have the weight of the cube, W. We have the force indicated on the spring scale, which is Q. And because it's submerged in a fluid, we have an upthrust force, U. So assuming that it's also in equilibrium, so the forces up is equal down. So it's very similar. But again, we are going to do substitution of U, or the upthrust force, is the density of the liquid, in this case oil, times G, times the volume of the cube, is equal to W, which is the weight of the cube. So I'm going to rearrange in terms of the density of the oil. So now I have the density of the water and the density of the oil expressions. So again, the question is asking the ratio between both densities, and we have both expressions. So now the density of the oil over water is, the oil is this one, right? And the water is this. So what we are going to do here is we have a fraction over a fraction. So this remains where it is, times we are going to invert the denominator. So the volume of the cube is the same and G is the same. So we are going to go ahead and cancel those two terms. And what is left is the density of the oil over water is this expression. So the correct answer is D. This question is from October-November 20, paper 12, question 15. A cylindrical block of ice of cross-sectional area 12 square meters is floating, partially submerged in the sea. The density of the seawater is 1020 kilograms per cubic meter. A polar bear of mass 400 kilograms steps on the block of ice. The block of ice sinks a vertical distance d. What is the value of d? So I want to start with this statement, the section of this statement where the cylindrical block of ice is floating and partially submerged in the sea. So this is an indication that we need to use the equilibrium forces formula. The submerged portion of the iceberg corresponds to the volume of seawater displaced, the blue shaded area. Assuming the submerged section of the iceberg has the same cylindrical shape as the visible floating portion, we can calculate the vertical depth, d, of the submerged iceberg using the formula for the volume of a cylinder, which is the product of the cross-sectional area and the vertical depth. The iceberg is floating, which means the forces acting up is equal to the forces acting down. So we have as force down the weight of the bear, and forces up we have the upthrust force. So F up is equal to Fg. Now the formula for F up according to Archimedes' principle is the density of the water times G times the volume displaced, which is equal to the volume of the area submerged, equal to the mass of the bear times G. So the volume of the water displaced, which again is equal to the submerged portion of the iceberg, is equal to the mass of the bear divided by the density of the water, because I cancel both G's. The mass of the bear is 400 kilograms, the density of the water is 1020, so the volume of the water displaced, or the volume of the bottom part of the cylinder, is 0.392 cubic meter. Now to calculate the distance that we are looking for, the vertical distance, we are using the formula of a cylinder, because we are assuming the part that we don't see is also cylindrical. So the vertical distance d, this part right here, is the volume divided by area, cross-sectional area. So the volume is 0.392. The cross-sectional area is 12 square meter. So D is 3.26 centimeters. So the closest answer for this solution is B, 3.3 centimeters. This question is from May-June 2020, paper 12, question 13. A pipe open at one end floats in a liquid as shown. Again, floats. So we need to equalize forces here. Some point. The cross-sectional area of the pipe is 0.012 square meter. The weight of the pipe is 32 newtons. What is the density of the liquid? So the shape of the pipe is usually cylindrical. So which means that we are going to be looking at the volume of a cylinder. So here we have the weight of the pipe, which is 32 centimeters. 32 newtons. And we have a updraft force because is floating in a liquid. Okay, so which means the F up is equal to Fg. So the updraft force is given by the density of the liquid times G times the volume displaced, which in this case is the volume of the cylinder. So the density of the liquid, because that's what we are looking for, is rearranging this is the weight of the cylinder divided by G times volume. So let's go to the other side, I don't have more room. So the density of the liquid is the weight of the pipe is 32 newtons, G is 9.81. Cross-sectional area we have 0.12 and the height is 0.3. So let's go ahead and do substitutions. And the density of the liquid is 906.1 kilograms per cubic meter. So the best option is B. So this is the last question and I hope you are still here. So this is from October-November 18, paper 11, question 13. A vertical tube closed at one end is immersed in water. A column of air is trapped inside the tube. The density of water is 1,000 kilograms per cubic meter. What is the difference between the pressure of the air in the tube and the atmospheric pressure? So the question is asking the pressure at this depth, which is the density of the water times G times this height. So the pressure is, the density of the water is 1,000, G is 9.81, and the height or depth is 20 centimeters plus 30, because that's the difference between the atmospheric pressure and at this point right here. So in meter is 0.2 plus 0.3, and the product of this is 4,905 Pascal. So the best answer is C, which is 4,910 Pascal.